All right, this is my solutions video for the second unit that we covered. There will be a separate video. You might have to look at flipping physics to kind of go over the concepts, but this is me working the problems on the second exam of semester 2. What is the angular speed in radians per second of a flywheel turning at 1,025 revs per minute? So 1,025 revs per minute. Per is a division, and now we need to get it into radians per second. So this is basically a conversion problem. Let's see. So we know that we have 1 rev, and let's see, what are they needed in radians? So 2 pi radians. And so we have 1 rev equals 2 pi radians, which also equals 360 degrees. So there's my conversion factors. And then I also know that 1 minute equals 60 seconds. And now all my units cancel except for radians per second. And I should get to 107.3. And that's the answer to the first one. Through how many degrees does a 45 rev per minute turntable rotate? So I want to know they're looking for delta theta in degrees. And so I want to, it's again, I can use equations or I could also use units. 45 revs per minute. And I want my answer to be in degrees. I need my answer in degrees. So I got to get rid of my minutes, so that's 25 seconds. I put my time on top. Now we'll have to convert, and then I got to get revs into radians. So let's do that. We got 1 rev, and that 1 rev equals 2 pi. Oh, we don't want radians, we want degrees. So 1 rev equals 360 degrees. And now I've just got to convert, get the minutes and seconds to cancel. So I know that I've got 60 seconds equals 1 minute. And so now my minutes cancel, my seconds cancel, my revs cancel, and the only thing I'm left with is degrees. Plug that into your calculator, you get 6,750 degrees. Everything on top is multiplied, and then you divide by 60, and there's your answer. We got a puppy that's running in a circular path with an angular speed. So we've been given omega. Omega is 2.4 radians per second. How long does it take the puppy to complete 1 revolution? So omega is equal to change in theta over time. 1 rev, what they're asking for is they gave you 1 rev, that is the, delta theta. They just gave it to you in units that we're going to have to convert. So delta theta they gave me was 1 rev, which equals 2 pi radians. So I'm going to rearrange this equation on the for the angular speed for let me change that here, delta t. So how long is what they wanted to know? So we need time. So change in time is equal to the change in position over the angular speed. And all the units have to be correct to get my answer in seconds. So delta theta was 2 pi radians. The angular speed was 2.4 radians per second. That second's going to end up back on top. And if you plug that into your calculator, you're going to get 2.6. It looks like 2 seconds. And that makes sense because they asked for how long. When a washer machine is turned off, its angular speed decreases from 20 rads per second to 14.3 rads per second in 5 seconds. There's your 3 variables, 5, 4, 3, 2, 1. 1, 2, 3. Now, what are those variables? Well, the initial angular speed was 20 radians per second. The final angular speed was 14.3 radians per second. And the time was 5 seconds. They want the average angular acceleration. This is a 5, 4, 3, 2, 1 problem. And I can use this equation That's alpha. Or I could use the definition of alpha. Same thing. It actually, this equation was derived from the definition. So change in velocity, angular velocity divided by time will give me the angular acceleration. The change is the final 14.3 minus the initial, which is 20, and that's in rads per second. I'm going to divide by second, which will give me rads per second squared, which is what I expect for an angular acceleration. If I plug that in, I will get a negative 1.14 radians per second squared. Makes sense that it's negative because it's slowing down. As you start riding your bike, the wheels begin at rest. So angular initial is 0. Velocity initial, the tangential velocity on the edge of the wheel is also 0. It has an angular acceleration of 5 rads per second. What is the angular speed of the wheel after 6.1 seconds? I've got 1 variable, 2 variables, 3 variables, 5, 4, 3, 2, 1. So I know angular speed initially. I know angular speed final is what I'm looking for. I have time is 6.1 seconds, and I was given the angular acceleration as 5.0 radians per second squared. Again, I can use my first equation, that's plus alpha times time. I'm now solving for time, which will be this. Time is, oh no, I'm not solving for time. I'm sorry. I'm solving for the final speed, the final angular speed. The initial angular speed was 0 plus 5 rads per second squared times 6.1 seconds. Rads per second squared times seconds will give me rads per second, and that's exactly what I should get for something that's asking for angular speed, 30.5 rads per second. All right, now we're moving into circular motion. I have a cart. Anytime I go through a curve, I need to pay attention to the fact that I'm no longer on a flat surface. So we're going to draw a free body diagram acting on the student when the ride is at the first dip of the ride, point A. So we're located at point A. Here is my dot. This is the student sitting in the chair. And we're going to have a force normal upwards, and we're going to have a force of gravity downwards when they're at point A. Now, the force normal has to be greater than force of gravity in this case, because otherwise we wouldn't be turning. We have to have a centripetal acceleration inward. So we're at the bottom. We must have centripetal acceleration inward. If there is an acceleration, that means the net force is in the same direction as the centripetal acceleration. So net force, that means the total force is added up. So I need more force upwards than I do downwards. All right, determine the normal force. So this is where students will try to go, well, force normal equals Fg. That is not correct because we're turning. Force normal has to be greater than Fg at this point. So we have to use Newton's second law, which is the sum of the forces inward, I'm on a circle, is equal to m times AC. Inward forces are positive for force normal minus force of gravity, so I'll just replace that with mg, is equal to mass times, now AC is a centripetal acceleration and it has v squared over r as one option, or r omega squared. Well, what did they give us? They gave us a linear speed. So we're going to use the linear definition of centripetal acceleration, so v squared over r. What have we been asked for? We've been told to find force normal. Now, there's only one unknown. I need to rearrange this equation to find force normal. So force normal is equal to mv squared over the radius of the circle, which is the radius of curvature of that dip, plus mg. So if I plug all those in, I think in my problem, what did I use? 9.8. On your exam, you can use 10. I used 9.8. So, what did I do wrong? Oh, okay, sorry. I got lost on my work. Okay, so force normal is equal to, it will be, the mass of the student is 65 kilograms times the velocity is 17.5 meters per second. Don't forget to square it. Divided by the radius of curvature was 8.2 meters. Then I have to add the force of gravity to it, which was, I used 9.8 here, which you don't have to, but, and then force normal is equal to 3065, and that is in newtons. Now we're looking at point B. Here's the dot. The person is, if you can imagine, if you drew a picture up there, there's still a force normal upwards. Now force of gravity has to be larger than force normal, because there has to be a net force downward towards the center of that circle. Not that I needed you to draw the length of the vector correctly. I didn't ask for that, but I'm just using this as a teaching moment or review moment. Anyway, determine how fast the roller coaster must be traveling for the student to have a feeling of weightlessness. Well, if force of gravity is not going to change, okay, because the Earth's magnitude of the force of gravity from the Earth doesn't impact, doesn't change. The Earth's mass is there forever and ever and ever. But the faster you go, what do you feel? Force normal is what you feel. And so in order to feel weightlessness, you're going to essentially go faster and faster and faster till finally you feel like, oh my gosh, I'm flying off the car seat. And so what happens in that moment is force normal at that nanosecond goes to 0. So we're still going to sum the forces inward, just like what we did before. Force of gravity this time is positive because it's pointing towards the center of the circle. Force normal is pointing outward, so it's negative, equals mv squared over r. I chose that definition because they asked for how fast. They didn't ask for angular speed. We're just going to set force normal equal to 0 in this case, and then move everything around and solve for velocity. Velocity is equal to rmg over m, which will simplify into rg, which will then equal 13.7 meters times 9.8 meters per second squared. All of that is under the square root, and that will equal 11.5 meters per second. So right at the nanosecond, you hit 11.5 meters per second. You will, in this the curve at part B, because the curve is different, because the radius of curvature is different, you'll start to feel weightless. All right, 7. A 0.5 kilogram toy is attached to the end of a 0.8 meter very light string. The toy is whirled in a perfectly horizontal path. Kind of hard to do, but just imagine perfectly horizontal. All right, no angle whatsoever. And here's the tension force there. Draw a free body acting on the toy. So if I drew a dot that represents that, I would have force of gravity down, and I would have force of tension that's pointing towards the center of the circle. Determine the tension of the string if the angular speed of the toy was 8.8 radians per second. Well, the only way that I can determine the tension is to sum the forces inward. It's equal to mass times centripetal acceleration. Force of tension is the force we're looking for. It's pointing inward. It's positive. There's only one force in the inward direction. There's no forces additional other than force of tension. They asked for an angular speed, or they gave me an angular speed. So I'm going to use omega squared times r. Let's double check. AC equals v squared over r equals r omega squared. Yeah, same thing. And now I should be able to solve the problem directly because I have everything I need. The mass was 0.5 kilograms. The angular speed was 8.8 radians per second. Don't forget to square it. The radius of the toy was 0.8 meters. If you plug that into your calculator, you'll get 30.98 newtons. All right, a 500 kilogram race car drives through a curved section of a horizontal track with an unbanked arc of radius 50 as shown in the figure. The coefficient of static friction between this roadway is and typical tires is 0.65. So they just gave me mu sub s is equal to 0.65. They gave me the mass of the car was 500 kilograms. They gave me the radius of the circle that the car is turning through as 50 meters. That's all they gave me. Draw a free body diagram acting on the car. Should have been more specific at that location. And so if I draw a free body diagram acting on the car, in the y direction, I have force normal. In the downward direction, I have force of gravity. The only thing that's preventing that car from flying off that circle is the force of static friction, okay? What force is creating the centripetal acceleration? Well, here's the axis of rotation inward. And so if I'm looking again at the side view, there is a force of static friction pointing inward. And so the answer is force of static friction. What is the magnitude of this force if the cart is traveling at 14.0 meters per second? This is not at the maximum. I just didn't tell you it was about to slip. So the force of the static friction at maximum is mu sub s times force normal. We're not at that point, so we're something less than that, and we can calculate what this is, but we don't know where we are. Force of static friction has a value that goes up, 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 hits max, and then goes down. We're somewhere in this region, and we don't know what that number is, but we can solve for it using Newton's second law applied to the situation. So Newton's second law states a forces inward is equal to m times the centripetal acceleration. Inward force is force of static friction. So that's the one we're looking for, mv squared over r. Well, we know the velocity that they're asking about, we know the mass, and we know r, so we can solve this way. 500 kilograms times 14 meters per second, don't forget to square it, divided by the radius, which was 50 meters. And then we know that that is 1960 newtons. Now, what would be the maximum driving speed for this horizontal curved track? Now we're at the maximum. Same problem. This time we are looking for the speed. So we're looking for the maximum force of static friction. So, or we get to use the maximum force of static friction. So we want the force of static friction max is equal to the mass times the maximum velocity squared over r. Now I can use the definition of the force of static friction since I know everything. So I have, let's see, that will be equal to mu sub s times force normal, which is mu sub s times mg. How do we know that force normal is mg? Because the two y values have to equal each other. Forces have to cancel each other out. And that is equal to mv max squared over r. Now I can rearrange for velocity, and I will get velocity is equal to mu sub s mg divided by m times r. So m's will cancel. This is square root, by the way. And I will get the square root of mu sgr. If you plug in the numbers correctly, I used 9.8, by the way, I'll get 17.85 meters per second. Okay. Give you a second. Okay. Number 9. A 65 kilogram person is camping, gazing at the moon. How large is the gravitational force on that person due to the moon? Now, that means we got to use the big G equation. Force of gravity is equal to G m1 m2 over r squared. Newton's second law states that every object attracts every other object using this force of gravity equation. Now, the person is one of the masses. So I've got 68 kilograms is one of the masses. The moon is what we're asking about, so that's the other mass. So I've got the mass of the moon. The distance between the two is given to me as 3.82 times 10 to the 8th meters, and don't forget to square it. And then we know that this is a constant, which is 6.67 times 10 to the negative 10, and then all of those units. So if we use our calculator correctly, this is a calculator challenge. By the way, when I enter in a scientific notation, I'll hit 6.67, and then I'll use the double E, second function double E, and then I only have to hit negative 11. It knows that that is to the base 10. 68 kilograms times 7.35 times 10 to the 22nd kilograms divided by r squared, and r is 3.82 times 10 to the 8th. All of that is squared, okay? And if you plug that in, you will get 5.74 times 10 to the negative 8 newtons All right, what is the magnitude of the gravitational force acting on a 50-gram student due to another 59 kilogram student? Same exact equation. So we got 6.67 times 10 to the negative 11 times 59 kilograms times 59 kilograms divided by 2 meters, and don't forget to square it. That's going to be a really small number. Where is it? Uh-oh, I lost it. Sorry about that. Okay. Apologize for the confusion. The force of gravity in problem number 9 turned out to be 0.00226 newtons. This one turns out to be the really small number of 7.4 times 10 to the negative 8 newtons. I apologize. Okay, extra credit on this test. This, again, won't be on the exam, but I'll show you. We got a graph of angular speed versus time. So we know that the slope is equal to fishy thing because it is in radians per second squared. So angular acceleration is slope, and the area is equal to the change in theta, which is displacement, and that is in radians. Angular acceleration at 2 seconds, well, I can find the slope of that line since the slope is constant, and so the slope of that line is equal to 1.5. So we just find the slope. I don't care which points you use, you'll get the same answer. And you should get 1.5 radians per second squared. Change in angular displacement. So this one is a little bit tricky. I need an area of the triangle and I need the area of the rectangle. So this is area 1 and area 2. The triangle is 1/2 the base, which is 4 units. Upwards is between 2 and 8, so that's 6. There's 1/2, that's area 1, plus the area of the rectangle, which is base times height, so 2 times 4. So 2 times 4. And I will get 20 radians. And that is the area bound by the line of interest and the time that we're talking about and the x-axis. And it concludes my review of that exam.